I'm going to talk about Galilei and his law of falling bodies. We talked about this yesterday, and we're going to be learning a lot about falling bodies. He basically discovered this law by experimenting with balls rolling down inclined planes. The way objects fall is pretty fast to be able to time them. It turns out that any object that has a uniform acceleration follows the same patterns in terms of distances that it falls during successive time intervals. Here's what that means. If an inclined plane, it's a ramp, right? All right. So let's start off and roll a ball down the ramp here. Starts off at rest. Now, the time units that you use doesn't matter. You could be measuring time in minutes. On the planet Oingo Boingo, they measure time in chronons, and some other place in the universe they measure time in units of Rice Krispies. It doesn't make any difference what your measurement is. It's the proportion that's important. So after 1 unit of time, right, on the Earth it would be like 1 second maybe. I'm just going to put 1 unit of time. And let's say that at that time, the distance that has rolled down this incline, let's just call it d. Okay? And d could be meters, it could be inches, it could be miles. It's a distance. Any unit of distance will do. Then, during the next same time interval, it's going to move farther because it's gaining speed. So this is after 2 time intervals, so t equals 2 whatevers. The distance it falls from here, or rolls from here to here, will always be 3 times the initial distance, so 3d. Then let's another equal time interval, so this is after t is 3. I guess I could say 3t might be easier. The distance here is going to be the next odd multiple of d, so 5d. Just one more here, all the way down here. So after 4 time intervals, the next odd multiple, let's see, so 1, 3, 5, 7d. And the steepness of the incline doesn't make any difference. You could even imagine the incline being straight up and down, and then it's in free fall. Falling bodies obey the same ratios. So, also, check this out. If I look at the total distance it's falling, so after 1 unit of time, it's d. After 2 units of time, the total distance is d plus 3d, so 4d. After 3 units of time, the total distance is d plus 3d plus 5d is 9d. Right? And then the next one, guess what? It's going to be 16d. And 1, 4, 9, 16, those are the perfect squares. Those are the squares of the first 4 integers. So distance increases according to time squared. Here's one way we could write that. Behavior of objects with constant acceleration. For constant acceleration, the distance fallen, I'm going to use an x here, is proportional to t squared. A little fishy there. That's different from equals to. It means it is proportional to the square of time. we could write this a little bit differently here if you want to. The distance that it falls is equal to a constant times t squared. That's a constant. That's just a number that doesn't change. And so it turns out that the numeric value of that number is just going to be the distance that it falls after 1 second. So consider an object that is in free fall near the surface of the Earth. X is proportional to t squared. Remember that. The distance that it falls. Let's put a grid here. Okay, so now we're dropping something. And we're saying that X, the proportionalities are going to be the same whether it's rolling down an incline or being released from rest and in free fall. So it turns out that after 1 second, so after 1 second here, we did this the other day, last week outside, the distance that it's fallen here is 5 meters. Now you might be wondering, why is he using an X? I thought it was Y. Oh, wait, no, I thought it was D. Well, we can use a lot of different letters and variables to represent quantities. Typically, for motion along a straight line, the variable that's used to represent position is an X. If it's two-dimensional motion, X is left and right motion, and a Y is like up and down. All right. So don't let this confuse you. X is just its position. In this case, it's how far it has fallen. So then, well, using these numbers then, we just said, remember, that X is equal to a constant times t squared. Well, 5 meters is equal to a constant times 1 squared. So then, what is the constant c? In other words, 5 is equal to blank times 1. Yes, that's right. For objects falling near the surface of the Earth, the value of c is 5. And it has units of meters per second squared. So then our equation for objects falling near the surface of the Earth, finally, it is equal to this expression, x. And that's starting from rest. Is just equal to 5t squared. This tells you the exact position of an object if you know how long it's been falling. Easy peasy, lemon squeezy. All right, yeah, so x is 5t squared. So for example, suppose we drop something. And it takes, ploop, 3 seconds to hit the ground. And we want to know, how high is the building? See, look, watch out. Oh, no, I'm using an H to represent displacement. It's okay. It's a distance. With buildings, we usually talk about how high they are, right? It's the same thing as X. So this means that H is equal to 5 times 3 seconds squared. So that means that H is equal to, so remember that this unit here, that 5, it has units of meters over seconds squared times 3 squared is 9, and seconds squared, well, those are seconds squared. Look what happens dimensionally. The seconds squared cancel. And the unit left is meters, and 5 times 9 is 45. So the height of that building is 45 meters. All right? Let's try one more. Okay. This time, we are going to drop something from an 80-meter tall building. Right. That's a long way. Boop, boop. All right, so he's going to drop something from rest from 80 meters above the ground. And this time, what we want to know is how long does it take to hit the ground? How long will it take until it hits the ground? Well, it's the same equation. X is equal to 5t squared. Only this time, you know what x is. X is 80, and you're solving this thing for t. So 80 equals 5t squared, and then divide both sides by 5. All right, so that means that the 5 drops out on the right-hand side. And 80 over 5 is 16, I think. Okay, let's get our units right here, okay? So that 80, that's meters. And the units in front of the 5 were meters per second squared. And meters over meters cancel out. And 1 over seconds squared is seconds squared. Now take the square root of both sides. The square root of 16 is 4. And the square root of seconds squared is seconds. And the square root of t squared is just t. So it's going to take 4 seconds to hit the ground. There you go. Problem done. Thank you very much.